Hello and welcome to 10.3, the integral test. Today in this section we're going to be looking at another technique to determine convergence or divergence for series. We start off with non-decreasing partial sums. So suppose we have a series, an infinite series, where the terms are greater than 0. So all the terms are positive. Okay, for all n. Then we say that each partial sum is greater than or equal to its predecessor. Okay. Now, we would say here in the corollary that the series of non-negative terms converges if and only if its partial sums are bounded from above. Okay, so let's take a look at an example of this. We consider this series summation of from 1 to infinity of 1 over n. And so we would start off with 1 plus 1 over 2 plus 1 over 3, continues, so on and so forth. So now let's take a look as we look at all these terms. 1 plus 1/2 plus 1/3. Now what we could do is group together these terms in such a way to show that whether this group series will converge or diverge. So these are our first few series terms in the series. Okay, so we see that first term is 1, second term is 1/2. If we were to group together the third and the fourth term, well, this will be greater than, if we group these together, add them together, this would be greater than 1/2, right? If we were to put fourths, this would be greater than 2/4. If we were to group together the next four terms, if we're looking at eighths as the smallest fraction, 1/7 is definitely bigger than 1/8. So if we group together all four of these will be bigger than 4/8. Okay, and we can keep going with the next sequence of terms like that. So this is going to be unbounded, right? So what happens is there is no upper bound for these partial sums, because you see that they're going to keep adding to our original first two terms. They're going to keep adding numbers that are bigger than 1/2. Okay, so because these partial sums are not bounded, and I should say no upper bound, that this series would diverge. Okay, what about this one? Does the following series converge? So to compare this, we're going to compare this to the integral of 1 over x squared dx from, what do we have here? 1 to infinity, so 1 to infinity. Okay, the way the series works is, if we have our graph, the series will be a sequence of rectangles. We have 1/2, and then we'll have 1/4, and then 1/9, and then 1/16. Okay, and the actual curve itself will be this. If you picture the blue, it'll be much more, right? So what we're going to do is take a look at some partial sum. Right, so we have partial sum. If we do 1 over 1 squared, we'll have 1 over 2 squared, 1 over 3 squared, so on and so forth. So if we continue, this will be equivalent to our function notation f of 1 plus f of 2 plus f of 3 . Now the area rectangles, as you guys can picture, it's going to be less than the area under the curve, right? So we will say that this will be less than f of 1 plus area from 1 to n, however many rectangles. Okay, and then that will be equivalent to, well, f of 1 is 1. And you could extend this, instead of limiting it to 1, you could say this is going to go to infinity. And we've done this integral before, right? This one had a value of 1. And so that our partial sums are bounded by above the partial sums are bounded from above by 2. Okay, so therefore we know that this series converges. Okay, so let's take a more formal look at the integral test. So the series terms have to be a sequence of positive terms. Okay, and suppose that we get those terms by some kind of function, where the function is continuous, positive, and it's a decreasing function of x for all x greater than or equal to n, some positive integer. Okay, then we could say that the series and the integral both converge or diverge. Okay. So let's take a look at, in general terms, for the P series. So in our P series, what we want to do is compare this to integral from 1 to infinity of 1 over x to the P dx. Okay, so we would say this is integral 1 to infinity x to the negative P dx. Okay, so next, improper integral, right? So we do limit as b approaches infinity. Now we could integrate this x to the negative P it will be x to the negative p plus 1. And then we would divide by negative p plus 1. And then we would have to plug in our b and plug in our 1. Okay, well, the 1 over negative p plus 1, we could pull that out, right? 1 over negative p plus 1. Or you could say 1 minus p, doesn't matter. And then we would take the limit as b approaches infinity. And if we plug b in, this will become 1 over, right, because b would be here, 1 over x to the, or say b to the p minus 1. Right, if we pull out the negative, that becomes p right, so therefore that's going to go to the denominator as 1 over x to the p minus 1. Okay, and then minus, if we plug the 1 in, minus 1. Okay, and as we take the limit, so if we take the limit as b goes to infinity, this term would go to 0. So we have 0 minus 1. So we have 1 over negative p plus 1 times negative 1, which we could rewrite this and say this is 1 over p minus 1 if we distribute the negative to the bottom. Okay, so this is what we would end up with. So now if we think about this, if p is less than, let's see, let's think about this 1 second. So let's summarize this and we'll say that we know for this series, right, for the p series, if p is 1 or p is less than 1, series diverges. So if p is less than or equal to 1, series diverge. If p is greater than 1, then we would say the series converges. Okay, and we see that once we plug something greater than 1, if we plug 1 in, we get the undefined, no good. If we go less than 1, then it would diverge. If p is greater than 1, series would converge and become some kind of fraction. Okay, let's take a look at another example. The series, so we have n equals 1 to infinity of 1 over n squared plus 1. Okay, not a p series, but I would say pretty close to 1. So does it converge or diverge? Okay, so we could compare this to the integral version of this. Integral will be from 1 to infinity of 1 over x squared plus 1 dx. So again, it's improper integral. So we do limit as b goes to infinity. Now the 1 over x squared plus 1, that would just be arctangent of x. So let's integrate it. Arctan of x. And so we would say limit b approaches infinity, arctan of b minus arctan of 1. And then as b approaches infinity. So, for arctan of infinity, that would be what? Pi over 2? And then the angle whose tangent is 1, that would be pi over 4. And so when we subtract, we get pi over 4. So according to our integral test, it says that the series converges. Okay. We got pi over 4. Right? All it says is the series converges. Does not tell us whether it converges to pi over 4 or the sum of the series is pi. All it says here is that the series converges. Okay, let's take a look at a couple more problems. Determine the convergence or divergence of the series. Okay, so let's use the integral test again. So we compare the series to the integral version. So it'll be from 1 to infinity. And then just replace the ends with x's. So this will be x e to the negative x squared dx. Another way to write this would be integral x and then e to the x squared dx. Okay, so to integrate this, if we did u equals x squared and then du would be 2x. Here this would be of the form we have an x dx, so this would be 1/2 du. Okay, so this will be 1/2, and then we would do du over e to the u. Okay, applying the integral test. Again, improper integral. Limit as b approaches infinity. This will be negative 1/2 e to the negative u. And then we go from b to 1. Limit as b goes to infinity. plug in the b, negative 1 over 2e to the b plus, right, because we have minus a negative, 1 over 2e. Okay, so as b goes to infinity, this term would go to, denominator will get really big, so this will go to 0. So we would just end up with 1 over 2e. So since the integral converges, we would say that the series also converges. Okay, let's take a look at the second part of that. So for this one, we could compare this to the integral 1 to infinity of 1 over 2 ln x dx. Okay, so for this, we could do a u substitution. We say u equals ln x if u equals ln x, we can say x equals e to the u, and then dx would be e to the u du. Okay, so when we make the substitution, we would have e to the u du, that would be the dx, and then we would have 2 to the u. Okay, so basically we have here e to the u over 2 to the u, so this will be e over 2 to the u du. And so this is set up in a form where we have kind of like a to the u, and we're integrating that. So the format would be, we're going to do, so remember, do our limit. This would be 1 over the ln of e to the u, or e over 2. And then we'd multiply by e over 2 Okay, so now let's plug in the b, plug in the 0. Where do we have 0? Yeah, it's supposed to be a 0. Okay, so that means we would have 1 over ln e over 2 e over 2 to the b minus e over 2 to the 0 which will just be 1. So now as we take the limit as b approaches infinity, think about it, b is going to go to infinity. This is going to end up becoming a really, really big number. This will go to infinity. Okay, once you see it going to infinity, you know that this integral will diverge, so the series will also diverge. So I would say this one diverges. Okay, bounds for the remainder in the integral test. So we figured out a way to estimate the remainder using the integral test, and this will be the formula for it. You'll have n number of terms, so it'll tell you how many terms they want it for, and so the remainder you'll know is going to be an estimate of the area between the n to infinity integral and the n plus 1 to infinity integral of the same function. Okay, so let's do an estimate of the sum of the series using the inequalities and n equals 10. Okay, so here we have our series. We know that we're going to be using the integral. We will do n to infinity of 1 over x squared dx. Okay, so for this one we would say that this is going to be a limit as b goes to infinity of negative 1 over x, because we could easily integrate that, and b to n. Okay, so if we plug in a b, this will be limit this will be negative 1 over b minus negative 1 over n, so that'll be plus 1 over n. Okay, and as b goes to infinity, as this goes to infinity, this will get really, really small. This will be 0. So we just end up getting 1 over n. Okay, so the idea is our sum is going to be less than or equal to the sum of the first 10 terms plus 1/10, and it's going to be greater than or equal to the sum of the first 10 terms plus 1 over 11. Okay, so now we can figure out the first 10 terms. Sum of the first 10 terms, this will be 1 plus 1 over 2. Oh no, this is 1 over x squared. So this is 1 plus 1 over 4 plus 1/9. And you keep this going all the way up to 1 over 100. And this will be approximately 1.54977. Okay, so therefore we could estimate that our sum is going to be less than or equal to 1.64977, and it'll be greater than or equal to 1.64068. Okay, and if we figure out like a midpoint of this error, right, just take an average of the two, we would say that the summation n equals 1 to infinity of 1 over n squared is approximately 1.6452. Okay, so interesting way to figure out the balance for the remainder, and this is how we would do it. Okay, any questions, just write me an email. Have a good day, have a good night, we will see you soon.